Okay, so today I wanted to read this paper um, because it's interesting. It's mixing, I guess, the notion of space-time distance with correlation. Which this comes from quantum mechanics, and this part comes from GR, general relativity. So I know a bit about quantum mechanics. I know even less about space-time distance. And I also know that people are very excited about trying to connect general relativity with quantum mechanics. I'd like to know why they're so excited about that. And so I thought that maybe this would be a good paper to read. Why is everybody so excited about connecting gravity and quantum mechanics? All right, so the paper is called Replacing the Notion of Space-Time Distance by the Notion of Correlation. And it's by Akim or Achim. Sorry, but the last name is Kempf. And they are from the Department of Applied Mathematics at the University of Waterloo in Waterloo, Ontario, Canada. And this was published in Frontiers in Physics. I'm not familiar with that journal. It's original research. It was published on the 19th of May, 2021, so fairly recently. All right, so let's read the abstract. Space-time is conventionally viewed as a stage on which actors in the form of massive and massless matter move. In this study, we explore what may lie beyond this picture. So, what if we go beyond this picture? What are we going to find? The starting point is the observation that quantum field fluctuations are the more strongly correlated the shorter their space-time distance. All right, quantum field fluctuations. So if this is our picture of space-time, then and this everything else is vacuum. I can't spell vacuum. Then I have quantum field fluctuations, which means that let's say I have the position and momentum of this particle here, and I were to measure its position and I were to measure its momentum, these angle brackets are taking the expectation value with respect to the wave function. So this particle has some wave function, and if I do that, which is the same as this, it gives me kind of the average position of the particle. and here gives me the average, and the angle brackets around P gives me the average momentum of the particle. And so if I were to have a phase space of x, its position, and P, momentum. So this is what's called a phase space. You can also have this in classical physics. And this is going to be for the particle psi. So this is the phase space for psi. And I could just take a snapshot of psi at a given time and measure its position. And let's say it's here. That's, this is my position that I measure, one instance of it. And then I also can measure its momentum. And maybe I get this value. Now, if you know about quantum mechanics, you know what I'm saying is nonsense, because I can't measure the position and momentum at one instant simultaneously. But just for this analogy, let's just forget about that for a second. And well, it'll be, so classically, this is what you'd get. You get just this point in phase space for your particle at a particular time. And well, let me draw up here a different phase space that people might be familiar with. Well, maybe in phase space your particle does something like this. Maybe it moves around in a circle as a function of time. I think that's like a harmonic oscillator. I can't remember. But the x squared plus p squared is just some constant. I think it's something like that. So you just get a circle, which means that you're oscillating. That could be like a mass on a spring. And this mass is oscillating, and the energy is constant. So in phase space, the mass can only live on this circle in phase space. Now, if you had some sort of loss in the system, like if this motion, or if the spring or whatever was losing energy, I don't know, from friction or something, I don't know, then this wouldn't be, x squared plus p squared would not be constant, and so you'd get some sort of decaying spiral over time as it loses energy. All right, that's an aside. This is just classically. So you think, okay, well, in quantum mechanics, maybe I would get something similar, but you don't. You actually get some sort of, this is a bad tool to, I don't know if there's another one, but these are supposed to be dots. So this is bad, but like, okay, so I'll just do a dashed line. Okay, so this dashed line is supposed to say that there's some probability to find the particle within this fuzzy kind of area, and there's no definite boundary for where you can find the particle in phase space. There's some uncertainty, and that uncertainty has to do with the Heisenberg uncertainty principle. Okay, so what that is, 1 second, I'll get to that. So the radius of the uncertainty so in general this is an ellipse, where this radius, I'll call it just delta x, change in position. And this here, this is a delta p, change in momentum. So kind of there's an uncertainty of where your particle can be that's proportional to delta x times delta p. That's kind of just the area of this uncertainty. And so you get something similar to the Cauchy-Schwarz inequality, or the triangle inequality. I don't know, something like that. But this area always has to be greater than or equal to some quantum parameter h bar divided by 2. And h bar is just Planck's constant divided by 2 pi, a very small number. But the point is, what was the point of all this? Oh, I'm talking about fluctuations. Jesus. Okay, so the point of all of this is that I've been calling this an uncertainty, and the product of the uncertainties, or the kind of the area of the uncertainty in phase space, has some minimum radius, or area. So you cannot reduce the uncertainty in this quantum particle below h bar over 2. So yeah, so you can't perfectly localize your particle in phase space. That's the point. Now, instead of calling this uncertainty, another way to talk about it is using the word fluctuation. So let's say, so now I'm not gonna talk about, can I erase this? Oh, I can't. Okay. So now I'm gonna forget about massive particles, and I'm gonna just talk about electric fields. So classically, if this was just, say, time, I looked at a classical electric field, which is just like a sine wave, let's say, and I looked at the amplitude of the field as a function of time for a certain point in space. Then maybe it just looks like this. And then what if I looked at its momentum? Which is just m times v. And v is the derivative. So the derivative is 0 here. It's going to be 90 degrees out of phase. And okay, I tried. There was an attempt. All right, but I can think of the field as just a particle of light going up and down in this waving matter, and then that's the electromagnetic or the electric field, let's say. And okay, so in phase space, if my x is going kind of like this, it's going, say this is 0, it's x equals 0, and this is p equals 0, and this is minus something, then x is going from positive through 0 to negative, like this, and p is going from 0 to negative to 0 to positive. Okay, so we have, in phase space, we have this circle. So this is the phase space for a classical electromagnetic field. For a sinusoidal wave. Right. Okay. And as you would expect from previous discussion I just did, that when you quantize the electromagnetic field, you would expect that instead of having just a single trajectory in phase space that's perfectly localized, you would expect to have instead this kind of fuzzy circle, right? It's supposed to be a fuzzy circle of uncertainty. And one way to think of that is that if I were to, well, I don't know if this is a good way or not, but take everything I'm saying lightly, loosely. I don't know, fuck, I don't know. So instead of just being this curve, if I were to zoom in on this, if I were to zoom in on a small part of this curve, instead of just being smooth or just whatever, maybe it's kind of just noisy like that. This is a very hand-wavy way of thinking of it. And so when you really zoom in, I don't like this analogy anymore, but there's some uncertainty. Yeah, I don't like this. But you get the flavor of what I'm talking about. So the whole point of all this is just to say that there's fluctuations. So if I were to take the, yeah, okay, so what's the point? Well, let me explain it experimentally. So imagine I had a photon detector, looks like this, and it's hooked up to a computer. That's a screen. And we're in the vacuum. Well, then you would expect, if the vacuum means that there's just no matter there, no light or no photons. Hang on a second. Yeah, there's no electromagnetic field, so there's no light. Then you would expect that if there's no light, then there's no photons. So then your detector would just give you nothing. So the detector, you'll have the counts and then time. This is the number of photons that are counted over time, or something like that. But actually what you find is that there kind of is something like that. So there is, and this is just some small number of counts. It's kind of constant over time. There's some average number. And this is the quantum field fluctuations. Well, not necessarily, but they're vacuum fluctuations. I don't know if that's the same thing. But these are the vacuum fluctuations. And it's just this idea that even when you remove all photons, all light, that there still is this background kind of dark count that's not noise, that's not thermal noise. It really is vacuum vacuum fluctuations. It's variations in the intensity of the electric field, even though there's no field there. So if I were to actually say that my electric field was something like sine of t, right? That sine function. Then if I did a quantum mechanical expectation value of its intensity, right? E squared is the intensity of the field. Then this would be, you would find that that's proportional, or let's just, I won't do proportional, just say it's equal. This is equal to the, something like the number of photons plus 1/2. I think it's something like that. But something like that, or maybe not 1/2. I forget. But the point is that there's a plus 1 or 1/2 here. And so if I do put some photons into my system that can be detected, then this count will be something like up here, right? Where this is n, and maybe down here is the 1/2. So that's n plus 1/2. Right? But then if I remove all the photons, so now I'm in the vacuum, I've removed everything, I still have this intensity expectation value of 1/2. So this is theoretically, this 1/2 dark count of the vacuum is predicted. So you can see it on your detector, and it's predicted in the theory when you quantize the electromagnetic field. So I mean that's vacuum fluctuations. But yeah, that was a pointless tangent. Okay, so then quantum fluctuations are more strongly correlated the shorter their space-time distance. I'm not familiar with this observation, but correlation just means that let's say that what I want to say, what is a correlation? Right, okay, so for example, let's say I have two particles, right? Or let's say, okay, instead of that, let's say I have here 2 particles get created from this point, 2 photons, let's say, and one of them goes this way, and the other one goes this way. They get created here. And this one has negative momentum, and this one has positive momentum. That's P1 and P2. So P1 goes in the, or I should call it 1 and 2. So the momentum of the first one is negative P, and the momentum of the second one is plus P, right? Now, what if I said, what is the expectation value of the momentum of the first one plus the momentum of the second one? Right? Well, this is just going to be equal to 0. Because on average, or actually I think this should be squared or something. I forget. But on average, we know that P1 is equal to minus P, and P2 is equal to P. So P1 plus P2 is going to be 0. So you say, well, yeah, so if I were to measure, so I guess on average you will get 0. Wait, how does it go again? It's if you measure the fluctuations or the uncertainty. Right, I think that's what it is. That's what it is that if you measure, right, okay, so if I take the position of the first one and the momentum of the first one, So if I measure the momentum and position of the first one, I will get some sort of fuzzy circle in phase space. And similarly, if I measure the position and momentum, of the second one, it's 2, I'll get something similar. So independently, particle 1 and particle 2 have kind of these fuzzy, uncertain position and momentum. But if instead I were to look at their position, and also if I looked at the oh, I think no, that should be, my bad. Yeah, they have equal momentum in magnitude. The magnitude of their momentum is equal. But their positions are different. Right, this one's going over to minus x, this one's going over to plus x. So but they have equal momentum, just in opposite directions. So if I took the difference of their momentum, you get 0. And if I added their positions together, I would get 0, because I'm assuming they start from 0. So now if I look at phase space, they're kind of combined phase space. Well, the difference of their momentum is going to be close to 0. Say this is 0. And the addition of their positions will be close to 0. So I'm going to get kind of more localized. So this will be minimized. This uncertainty will be minimized. Actually, probably the better way, the more illustrative way, is all right. So x1 minus x2 I don't really know what x1 minus x2 is, because x1 is minus, so x1 minus x2 is just going to be something like minus 2x. And if I don't know what x is, so if x is uncertain, so if x is uncertain by this big blue circle, that's how much is uncertain by, then the difference of the positions will be uncertain with a similar radius. So my uncertainty in x1 minus x2 is going to be large. So this will be the radius along the x. But the uncertainty in the difference of the positions is going to be small. So the radius of that will be small. So I'll have this flattened circle, or this kind of ellipse, in my phase space. So the point is that correlated, what that means is that the fluctuations in the momentum of the two fields is or the fluctuations in the difference between the momentum is reduced. They're correlated, right? So we'd say that the two momentum are correlated. And similarly, if I were to look at P1 plus P2 and X1 plus X2, well, this would just give me the reverse, or the rotated version. Now, this is what phase space would look like. Because X1 plus X2 will be approximately 0. But P1 plus P2 will be approximately 2P, which is uncertain. So we would say that in this sense, the positions are correlated because the sum of the positions is close to 0. So let's say somehow you said, oh, I saw particle 1 and it's at position minus 10. Well, that's correlated with position 2 because I can immediately say, well, particle 2 must have a position that's approximately plus 10 because I know they're correlated. And I could do a similar thing with the momentum of the two. So that's kind of the fluctuation part has to do with taking an expectation value of something squared, and the correlation is between the measurements of two separate things, something like that. All right. But I'm not sure why the correlation is stronger for shorter space-time distance. Because let's say if I were to take two entangled particles, for example, those entangled particles are strongly correlated, but it doesn't matter the distance between them. So I could have the particle 1 over here and particle 2 over here, and maybe they're separated by a large distance L. They're still perfectly correlated. So I can write their wave function as, let's say I can have two possible values of 0, 1 for each. I could write their wave function as 1, 1 plus 0, 0, for example, which is a maximally correlated state because when the state of, so there's only two possibilities here. When the state of the first one is 1, the state of the second one is 1. And when the state of the first one is 0, the state of the second one is 0. So they're perfectly correlated. There's no other option in their wave function. And this wave function, you can write it down irrespective of distance. It doesn't depend on L whatsoever. So I'm not sure what this observation is, that quantum field fluctuations are more strongly correlated the shorter their space-time distance. What that leads me to believe is that, let's say I have now I'm going to be really cartoony, but let's say I have a fluctuation here and a fluctuation here. Those are less correlated than these two fluctuations. So these two fluctuations are more correlated than these ones. Now I'm not sure why that is. Unless in some sense there's kind of like a strength of interaction. So let's say, for example, quantum field fluctuation, I'm just going to say, okay, that's photons, because photons are fluctuations or quantum particles of the electromagnetic field. So let's say I have a lattice, or let's say I just have some collection of photons that I'll draw as circles. And these are positioned in real space. I don't know space-time, so whatever. I guess you can write this as x and ct, let's say. I don't know. So these are just in some position. They have some position at some time. This is some space-time. Two-dimensional, so I don't know. And then I guess the statement is that they're correlated, right? So let's say if they're correlated, I'm going to draw a line connecting them. And we'll just draw some graph then. Okay, so just imagine that this is the graph. Maybe this one here is only correlated to this one. I mean, I could draw a fully connected graph, but I'm not going to mess things. And then I'll say, so there's other, so these are my quantum field fluctuations. These lines are my correlations, and I'm in some space-time. And so the length of these lines, so I haven't drawn things to scale. Let's do it to scale. So let's say that the length of the lines connecting them is actually indicating the distance between them. So maybe I have these two over here that are close. Well, they're at the same position, but they're separated in time. So it's just, this could just be a photon that's correlated with itself through time. I don't know if that's possible. And then maybe over here you have some other group. So these ones over here, these are going to be strongly correlated because their space-time intervals are, their distances in space-time are short. And I don't know if I've violated some sort of speed of light or something, probably have, but let's ignore that for a second. But these correlations will be weak, right? Because whatever, and there's a bunch of these connections here, you can see. These are going to be weak because the line is longer. So we could assign a value. So instead of doing this to scale sort of thing, you could just say, okay, say I have these 4 points, and now the length of these lines don't indicate distance, but I'll just put a weight on the edge. So maybe that's a 0, that's a 1, that's a 10, that's a 13, and so on. So 13 would mean that they're very strongly correlated, so they must be close. 0 means that they're not correlated at all, so they must be very far apart. So what it looks like is you have some graph of fluctuations with some adjacency matrix that gives the weights. And those weights are going to then give you, those weights will then give you kind of the distances between those fluctuations, which then is kind of equivalent to a metric, space-time metric. So these weights, I can collect these weights into some matrix. Maybe this is what they're going to do, some metric G, or matrix G, and then G11 here will give you the correlation with itself, which is probably 0. 1, 2 will be the correlation between 1 and 2, right, so on. So you have zeros all along here, and then some numbers, 2, all along here. And then so you could build up this G by measuring correlation. So correlations are equivalent, or correlations are proportional to distance. And we can measure correlations between photons, let's say, and therefore we can build up a notion of distance, space-time distance between the photons. All right, the notion of space-time distance can therefore be replaced by the notion of correlation strength. This suggests a new picture in which the abstract two-point and multi-point correlations are the primary structure, a picture which is essentially information theoretic. No clue what that means. In the low energy regime, the secondary notions of space-time and of matter would then emerge as approximate representations of the abstract correlators, namely in the form of Feynman rules on curved spacetime. No idea what this last sentence means. The discoveries of general relativity and quantum theory each required the abandoning of major misconceptions. Today, the fact that it has turned out to be extremely hard to unify quantum theory and general relativity suggests that at least one more major misconception will need to be overcome. But what deeply held belief about the nature of space-time and matter may need to be abandoned to clear the path for the development of the theory of quantum gravity? One belief regarding space-time and matter is that while they do interact, they are fundamentally different. So space-time and matter do not equal, they're different. So space-time, matter, they're in the same theory, and they can interact, but I guess we're going to go to a place where you have space, time, matter, all in one. With space-time representing a stage, which is itself dynamical, on which actors in the form of massive or massless matter move. The present study, which lays out ideas first presented orally in one, asks if the stage and actor's picture could be a misconception that needs to be abandoned. And it explores one possibility for what new picture lies beyond. Okay, so the idea is that you have a stage with particles on it, and the particles move. But I guess what they're saying is, what if there's really just one thing? It's not a stage, it's not particles, there's some other thing, whatever it is, and the rules for that thing give you particles, and they give you the stage, and then also how they interact. What is that thing? I don't know what this reference 1 is. Oral presentation at the workshop Interplay of Quantum Information, Foundations, and Gravity. Oh, so there is a video recording of this talk. So if you want to have a video recording of something similar to this paper, there's the address right there. Most of the results of the present paper were first presented in this talk. and it's exciting stuff. So maybe I'll watch that video. Okay, that was the introduction, very short. Chapter 2, probing the description of space-time of general relativity. For inspiration, we can take hints from some of the currently most successful descriptions of space-time. One general relativistic description of space-time is a pair mg, where m is a differentiable manifold. I think manifold is just your curvy space-time, I think. And G is a Lorentzian metric. And G tells you distances and angles, right? On the surface. Okay. That's a description of space-time is some manifold with a metric. Okay. And the metric tells you the distances and angles between points on the manifold. So if the manifold is just Euclidean space-time, just a sheet of paper, then the metric is x squared plus y squared equals, I don't know, 1, something. But then if you have a sphere, that's not the case anymore. Something like that. You have a different metric. You have a different metric. I think. I don't know. Equivalently, a space-time is often described as a manifold with Christoffel symbols gamma, capital Gamma, or a connection one form, omega. I don't remember what these are. All right. In mathematics and physics, the Christoffel symbols are an array of numbers describing a metric connection. What's a metric connection? The metric connection is a specialization of the affine connection to surfaces or other manifolds endowed with a metric, allowing distances to be measured on the surface. Blah, 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 blah. Something to do with the metric. Also, equivalently, general relativity describes a space-time as a pair, m sigma, where m is the differentiable manifold, and sigma, where sigma equals 1/2 g tilde x and x prime, is the sinh world function. Here, g tilde is the geodesic distance between the events x and x prime. And if I remember correctly, geodesics are the minimal paths light takes them. It's the path that light takes going the speed of light. Last scenario. Geodesic distance between the events x and x prime. as far as that distance is unique. The Singe function sigma contains all information about a spacetime since it allows one to recover its metric. So the metric is equal to the limit as the events get closer and closer, so as event x becomes equal to x prime, the geodesic distance essentially between them becomes this, just becomes some sort of derivative. Oh, no. I haven't taken the limit, no. It's the derivative. Oh, the derivative. Oh, I see. Yeah, if I take the derivative of the geodesic, if I take the derivative of the geodesic, and then I take the limit as those two events go to the same event, then I just get the metric. Okay, all right. For later reference, notice that equation 1 proves that knowing the biscalar function g tilde in an infinitesimal neighborhood of its diagonal is sufficient. Right, because as in the limit that these two events become the same, then x and x prime are equal, and so G just becomes G becomes a diagonal matrix. Okay. Finally, we should add that to complete the general relativistic descriptions of spacetimes, Einstein also provided an exact mapping between the mathematical concepts and concrete physical measurements based on rods and clocks. To search, all right, so I have to go now, so that is all. There'll be a part 2, I guess.